Thank you very much. So I'll be talking about population protocols. I apologize for my window not being entirely full screen here. I haven't been able to figure out how to do that and still be able to see everybody. So there's going to be a little bit of a border around the edge here. So I'm going to talk about the population protocol model, which has recently become fairly popular in sort of the PodC disk world. And I'm going to take a little bit of a historical approach about this because the model actually dates back to a paper from PodC 2004 that a bunch of us at Yale put together, Dana Angluin, Zoe Diamati, Mike Fisher, Renee Peralta, and myself. And we were looking at a model back then that was trying to model the kind of unpredictable interactions that you would get in some classes of sensor networks. So the motivation we imagined at the time was that you had a bunch of sensors that maybe had some limited radio communication capability and were implemented perhaps as smart RFID chips. And we imagined that they were attached to livestock or birds or something like this so that they did not have control over which other agents they would be close to. And so we were trying to devise a model that would cover situations like this where we had fairly weak agents with limited control over how they interacted with each other. And that's no longer the motivation that people tend to use for population protocols nowadays. Sensor networks have fallen a little bit out of fashion. So now we tend to describe this in terms of molecular computation, which I think is actually a better fit for how we design the model. Because the core idea of the model was that we would have these weak anonymous agents and that the interactions between them would not be under the control of the agents themselves. And this seems to be a fairly natural way of describing what's happening if you have, say, a test tube full of molecules and we imagine doing a computation where the computation consists of a sequence of reactions between these molecules, hopefully driving the global configuration of all the molecules together into some state that reflects some property of the initial input, the initial set of molecules. And you can think of this as a simplified version of a chemical reaction network, which is a theoretical model that's been around in theoretical chemistry since forever. The main difference between this and the full-blown chemical reaction network is that we don't assume that there's any particular reaction rate, and we ignore things like temperature and interactions involving more than two agents. So here's a kind of overview of the formal model itself. So we have a collection of finite state agents, which, on the left here, you can imagine that these are a bunch of molecules in the test tube that are mixed up in some way. And the steps of the computation are interactions, where an interaction involves two agents, which are given asymmetric roles. We think of one of them as the initiator of the interaction, one as the responder of the interaction. This is mostly just an excuse to include symmetry breaking in the model as a basic feature. And there's a joint transition relation, which I've depicted here as this table in the middle, where for each pair of possible states of the two agents that are interacting, there's an arrow that points to the resulting states that you have after the interaction occurs. This particular transition function that I've done here is a form of leader election. So if we imagine that the red agents are leaders or candidate leaders and the white agents are followers, the leader election algorithm here works by the very simple rule that if two leaders meet each other, one of them will drop out. And eventually, if we keep iterating this process, there's some other rules that allow leader bits to move around between agents, which can be helpful if, say, not all agents can interact with each other. But eventually, if we keep iterating this process, we hope to get down to a single leader and converge to a configuration where we have exactly one leader, which we can then hopefully use for some other purposes. And as with any sort of non-deterministic protocol, we need to establish some rule for who decides what interactions happen at each step. And here we assume that in the basic model that there's an adversary that makes that decision, but we'll impose a fairness condition on the adversary later to keep it from preventing us from making progress. All right, so one of the assumptions that we made in the early version of the model was that we had finite state agents, that the size of the states on the agent and thus also the size of the transition table did not depend on the size of the population. And mostly we did this because we were afraid of accidentally building Turing machines. So if you give the agents enough state that they can assign themselves distinct identities, particularly if they can get distinct identities in a sequence, then you can implement a Turing machine because you just appoint one of the agents to represent the finite state controller and appoint the other agents to represent the cells on the tape. And the finite state controller can just wait until it meets the appropriate tape cell in order to update it. And, this may be a fairly slow process, but allows you, just in terms of computability, to compute anything that you could compute with a Turing machine that had a tape proportional in size to the size of the population. So one of the reasons why we put in this constraint that said that we had finite states was we really wanted to avoid this situation because in a sense we already understand more or less what Turing machines can do. And we wanted to look at a model where there are still some interesting questions about what we might be able to pull off with it by taking advantage of the fact that we have this potentially massive parallelism between, large number of molecules or large number of sensors in the sensor network. And as an example of some of the things that we can do despite this finite state assumption, and we have this leader election algorithm that I described already, and I wanted to put this up again here because I wanted to talk a little bit about the fairness condition, which is what allows us to actually make progress. So in this picture, I've drawn the transition table on the left again here just to, so that we have it up here. On the right, I've drawn a picture of the configuration space, starting with an initial configuration where all the agents consider themselves to be leaders. And so here I have 3 agents with 3 different states. And each arrow here represents a possible transition to some other configuration resulting from 2 of the agents interacting with each other. So initially, the only non-trivial transitions we have are ones in which one of the leaders drop out, but then we can also have transitions between these configurations where the leader bits move around because these central transitions allow that to occur. But our hope is that eventually we get into this final strongly connected component here of states where we have exactly one leader. And what enforces that is that we impose a global fairness condition on the adversary, which says that if there is some configuration that is continuously reachable throughout the protocol, the execution of the protocol, then eventually that configuration will be reached. And it's eventually, so it could be a year from now, it could be 1,000 years from now, but we do put a constraint that says that eventually the adversary has to take pity on us and allow us to make progress. And typically in these protocols, all we can ask for in terms of completing the protocol is this kind of convergence property where we converge to a good state. We generally can't ask for detectable termination because the global fairness condition does not require that the adversary show us all of the agents immediately. So it's conceivable that with these 3 agents here, that there could be a 4th agent hiding out under the couch cushion somewhere. And eventually the adversary will have to show that agent to us, but we're not going to be able to tell when that occurs or whether there's a 5th agent or a 6th agent somewhere that we can't reach and can't see. So this is going to be a recurring theme with population protocols, is that we're going to be looking at protocols that converge, but we aren't necessarily going to be able to compose them together or iterate them because of this issue of not being able to detect termination. But we can do additional computation in some cases by piggybacking it on top of the leader election protocol. So here is a protocol for computing parity. And the essential idea is we're just going to add some additional information to the leader bit. So in addition to carrying around this property of being a leader, in this case a blue or red node, and a non-leader, the white nodes, I'm also going to keep track of the sum of the parity values of all the nodes that coalesce together into this particular leader. So here initially everybody is carrying essentially a 1. So if we think of the red nodes as 1s and the blue nodes as 0. And then when 2 of these nodes meet, they're going to combine whatever parities they had, add them together mod 2, and that will give the new parity for the new leader that gets created. So here, as we cancel these guys out, we end up with configurations where we have 1 red node and a blue node representing the 2 different possible parities. And when we finally reach this terminal strongly connected component here, the single leader, by virtue of this invariant that we're maintaining throughout the execution of the protocol, that the sum of the parities is constant, is going to be carrying around by itself the total parity value of the original set of agents. And this works, in this case where everybody starts off with a red node. It would also work if some of the nodes started out red and some started out blue. And in general, this kind of computation is what we're looking for, what we call a stable computation, where you eventually reach the right answer, and then from that point on, it doesn't change. In this particular case, I've adopted an output convention that it's enough for a single agent to know what the answer is. An alternative that you can do is to say that we need every agent to know what the answer is, but these are essentially equivalent because we could always add some extra state and have the followers just remember the state of the last leader that they met. And eventually, once we do get down to a single leader, it will at some point go and talk to all of the followers because of the fairness condition and thus propagate the value through the rest of the population. Maybe slow, but it will guarantee that we eventually do stabilize. This is not quite self-stabilization in the sense that that's often used because we are assuming that we have a good initial state, so we're not required to converge if we start in a bad initial state, but it is stabilization in kind of a weaker sense. We can also solve problems like majority. Here I've omitted all of the non-interesting transitions. Basic idea of majority, if I want to know are there more red nodes or blue nodes in the original population, assuming that there is a strict majority in favor of one or the other, I just have them cancel each other out. Whatever nodes survive are going to carry the majority value. And again, we can have the non-participating nodes copy that value if we want all of the nodes to know what the majority is. And these two building blocks, these sort of coalescence-based algorithms like we had for parity and these cancellation-based algorithms like we have for majority, by building on these, we can actually build pretty much anything that you can do in this model. So there's nothing special about mod 2 for parity. We can do the same kind of coalescence mod k, where you just store a value mod k in addition to your leader bit. And so we can get mod k for any fixed k. We can't do it for k that depends on n because nothing can depend on n here because of the finite state assumption. And with cancellation, we can get less than an equality. And various other things like addition, we can simulate just by renaming. And we can also combine protocols together. So if I have a protocol for computing some predicate f on the input and a protocol for computing some predicate g, I can run those in parallel, with each agent having part of its state allocated to f and part of its state allocated to g. And then when we get to the end and everybody has the output of f stored somewhere and the output of g stored somewhere, we can just combine those together locally at each agent. And this gets us essentially arbitrary logical formulas built on top of these basic mod k and less than predicates. And that turns out to be enough to implement all of first order Pressburg arithmetic, which is the first order theory of the natural numbers with addition and equality. And simple example of this would be, we can ask questions like, is there a certain rational proportion of the initial input agents have a particular color as opposed to some other color? And the nice thing about this is that this all right, okay, so let me actually mention an alternative characterization of this before I jump into this, because this will be handy later. An alternative way of looking at this is that this first order Pressburg arithmetic formulas are known to give us what are called semi-linear predicates, which can be expressed as unions of these cones where we have some base vector. Here, say the base vector says we have one x agent and 0 y agents. And then we have some additional vectors that we can add on non-negative integer copies of them in order to get other values out there. Here I've got a union of two cones, and it's not terribly hard to see how you can build the basic things like parity and such. This gray cone here is essentially implementing parity of the number of x agents with a constraint on the y agent, and also less than. And it turns out that anything you can define in the first order Pressburg arithmetic, you can convert to the semi-linear representation and vice versa. So these are equivalent to each other. All right, and the nice thing about these semi-linear predicates is that it turns out that the ability to compute semi-linear predicates is very robust over small changes to the model. So a lot of the early work on exploring this model was looking at, well, what happens if we change kind of the conditions under which it's running? So we showed in the original paper that you could compute all of these semi-linear predicates in the standard model. In later paper, we showed that if you assume that the input to the protocol only stabilized after some initial period of confusion, you could still compute the predicate on the ultimately stable inputs. And other changes to the model, like assuming one-way interactions or assuming a small number of agents failed, up to minor tweaks to what it meant to compute things, like in the case of agent failure, allowing you to compute the value of a input that might be slightly different from the actual input, given that you can't see the inputs of failed agents. These all turned out to give you the semi-linear predicates. And this ended up not entirely being an accident, because we managed to prove in 2006 that you can't actually do anything else in any of these models. That the semi-linear predicates are both what you can compute and the most that you can possibly compute. And the reason for that pretty much comes down to this issue of hidden agents sitting out there. A fundamental problem that we ran into early on with population protocols is that we can't do any kind of iteration. So if you want to compute something that's not semilinear, and kind of the classic example of this would be, say, multiplication. You know, I have a bunch of A agents, a bunch of blue agents, and I want to, or B agents, and I want to generate a bunch of C agents where the number of those is the product of A times B, assuming that fits inside N. There's a natural and obvious way to do that, which is just to make copies of the B agents, all of them, to C agents, and every time I do that, delete one of the A agents. And the problem is that if I try to do that during my copying phase, there might be some B agent out there that I'm supposed to copy, but I don't notice that it's out there. And I don't have any way of detecting it's out there given the limited abilities of these individual agents. And so this is kind of an intuition for why I get into trouble if I try and do these sort of iterative processes. And we actually managed to prove that anything that did require this level of, nested iteration, we couldn't do using essentially a pumping argument using some tools from partial order theory. All right. And so this, in some sense, made the model stillborn. We devised this model, we showed that it can compute semilinear predicates, then we showed that it couldn't compute anything else. And so what else was there to say? The model's done, it lasted 2 years and we have nothing else to do. Of course, researchers never stop at that point. There's always some way you can tweak your model to get more opportunities to prove results. And so there is this whole cottage industry for a while of looking at ways of extending or improving or adjusting population protocols so that you didn't run into this particular impossibility result. So one class of these involved adding more structure to the underlying protocol. All right, so one approach that was taken by Garraway and Rupert in 2007 was this idea called community protocols that said, okay, let's keep the finite state assumption and let's try and preserve as much of the anonymity assumption as we can. But what we'll do is we'll allow agents to remember who they've talked to. So I don't have the ability to do arithmetic on identities, but I might have the ability to remember some constant number of other agents. And so if I meet them again, I can say, aha, yes, this is the agent I talked to 3 steps ago, without otherwise having to rely on saying, well, this is a blue agent. I talked to a blue agent 3 steps ago, and it might have been the same blue agent. Maybe it was, maybe it wasn't. This model allowed me to recognize people out there. And the ability to recognize other agents gives you the ability, in a sense, to create pointers to other agents. And so Garraway and Rupert showed that if you did this, you could build a pointer machine. And pointer machines are known to be equivalent to Turing machines of, appropriately bounded space. So nice result, but again, we kind of hit Turing machines. And as soon as we hit Turing machines, we don't have anything else to say. Another approach that was done by Katsianakis, Mikhail, and Spirakis a few years later was this idea of mediated population protocols. This, in some ways, was a little bit stronger. The idea was that between each pair of agents, we would imagine an edge. And on that edge, there would be some state that the agents could look at. So not only would I recognize when I met you for the second time, but I would have some history of our previous conversation that we could both look at in deciding what to do next. And this turns out to be enough information to impose a lot of structure on the protocol, and they actually got an n squared space Turing machine by storing data on all of those n choose 2 edges. All right. And a third assumption, which was not motivated so much by trying to avoid these impossibility results, but which is actually fairly common in the sensor network literature, so which appears in a number of population protocol papers, is that we have somewhere a powerful base station that is equivalent to a Turing machine. In principle, this means that the base station could do all of our computation for us. So in terms of computational power, the rest of the agents are in some sense kind of irrelevant. But there are still a lot of interesting questions that came up here, and there's been a lot of work on asking, well, how can we use communication between the weaker agents out in the field, representing sensors or something, in order to pre-process information so we don't need so much communication directly with the base station. And the problem with all of these, if our motivation, primary motivation for this is imagining a test tube full of molecules, is that even though we can imagine ways of building all of these structures in other systems, for molecular computation, these can be hard to justify. It's hard to see how to fit all of this data in. So an approach that is slightly more friendly to molecular computation, but still a little bit implausible, is to add oracles of various kinds. So an oracle is some mechanism that allows us to kind of reach in and unilaterally change the state of one or more agents in response to some event occurring within the global configuration of the population protocol. So Mikhail and Spirakis had a proposal, a very nice proposal, which was that you could give a special leader agent, an agent in a special leader state, which a lot of these protocols have. what they called a cover time oracle. And the cover time oracle would allow the leader to detect when it had successfully talked to all of the other agents in the population. And this eliminates the missing agent hiding under the carpet problem, because I can now tell as the leader when I have in fact talked to everybody. And they showed that by doing this, you could play some games and turn your population essentially into a non-deterministic log space Turing machine, where the storage was done in unary, a trick that I'll actually talk about a little bit later. A little bit complicated to see how you would actually implement this, but you could imagine some external observer might be able to detect what's going on and might be able to tell the leader what is happening when you do this. I tried to generalize this a little bit in a paper from POTSI 2017 with the notion of what I called a clocked population protocol. Here, I didn't specifically allow the leader to detect when they had talked to everybody, but I included a more general mechanism that said essentially when the protocol got stuck, when the configuration wasn't updating for a long time, then some external agent could go in and send in a signal that would cause the protocol to jump out of that stuck state and realize that it had been running for a long time without making progress. And this turned out also to be able to get anything in non-deterministic log space. And it's an open problem whether or not it can do anything stronger than that. There's a possibility that might actually be able to get alternating log space, but I wasn't able to prove that myself one way or the other. And again, a related version of this that wasn't directly aimed at sort of computational power, but has the same kind of structure. Very early work, Mike Fisher and his student Hong Zhang had this paper in Approximate 2006, where they said, okay, a lot of the times we're interested in leader election. We can't figure out any way to do self-stabilizing leader election, because if you start with no leaders, there's nobody who can detect that. And so they said, well, let's just throw in an oracle that says if there are no leaders, we'll let somebody know so that we can jumpstart that. And so there's been a little bit of work on sort of self-stabilizing population protocols based on that kind of idea. And the tricky thing here again is that all these models require something a little bit more than just a test tube full of molecules. At minimum, you have some experimenter sitting on the side of the test tube that's willing to like flick it a little bit when things start going wrong. Right, which, as I understand it, people actually do chemical reactions. They do have graduate students who sit next to the test tubes and watch them, and if things go wrong, they're willing to like tap on them or turn the blender on or something like that. But we don't necessarily want to bake that into the model itself. All right, so the third option, and the one that became very popular as a result, I think, because we could tell a good story about this with molecules, is to replace the notion of adversarial scheduling with randomized scheduling. This completely breaks the impossibility results, because now the adversary can't construct these very bad executions in which terrible things happen, because the adversary has no real power. It's just all it can do is pick up a pair of agents chosen uniformly at random, bounce them off against each other, and see what happens. And the nice thing about this, in addition to fitting very well in sort of the models that chemists have been using, is that it gives us a notion of time that we didn't really have before. Before, we had this fairness condition that said that certain things happened eventually, but eventually isn't something we can measure. Eventually could be millions of years, we don't know. But now we can talk about progress in terms of steps, because the amount of time that some sequence of operations takes is in principle predictable, at least in expectation. So for example, if we look at this leader election algorithm, we can calculate, what the expected time is between until we get a collision between the next two leaders, given a certain number of leaders in the population. If you add all this up, it ends up being dominated by the time for the last two leaders to randomly meet each other. All right. And the time for that to happen is roughly, the probability that it happens at each individual step is roughly 1 over n squared. So the expected waiting time for that to happen is going to be about n squared interactions. Now, by convention, almost all of the results in the population protocol literature will take a time like that and divide it by n. To get parallel time. There are two reasons for this. One of them is it makes our protocols look better, because we lose this factor of n. The other reason is that this is actually the measure that chemists traditionally have used in chemical reaction networks. They tend to assume that all of the molecules are interacting at a fixed rate. And so that naturally corresponds to looking at a linear number of interactions per time unit when we translate that back into this population protocol-like model. It also gives us a little bit more, cleaner description of what the time complexity is of a lot of protocols, because a lot of them end up running in log n or log squared n parallel time. And if we had the extra n in there, that would just be distracting. All right. Another thing we get out of this is that we get more power, because if we have predictable, at least somewhat predictable stochastic processes driving our population protocols, we can now have the ability to have, say, a leader go and wait long enough to find that last missing agent that it was missing before, because you can only go so long before you actually are going to run into all of the other agents in the system. And this is something that we actually did in the original POTC 2004 paper. Oddly, we did not refer to this version of the model as population protocols. There was kind of an argument among the co-authors on this paper of whether we should call this model population protocols or conjugating automata. And population protocols kind of won out because it has more alliteration, I think. But but our compromise in the original paper was we would use conjugating automata to refer to this other model where we had random interactions. And conjugating had something to do with bacteria exchanging RNA or something like that. But anyway, but this other model, which now generally just gets described as population protocols with random scheduling. So in this model, because you've got randomness, now when you elect a leader, the leader can go and build itself a clock in some sense of its own. The rather crude mechanism that we had in the original paper is the leader appoints a deputy, just finds some other agent and puts a mark on it saying you're my deputy. And now what the leader can do is the leader can detect when a polynomial amount of time has gone by just waiting until it sees the deputy, say, 5 times in a row. All right. And it could get unlucky and see the deputy 5 times in a row just because it happened to draw it that quickly. But each time it does one of these samples, there's only a 1/n chance that it actually does encounter its own deputy. And so if you see your deputy 5 times in a row, that's something that probably happens only about end of the 5th of your own steps, after about end of the 5th of your own steps, on average. And so you can make an argument that with at least reasonably high probability, you're not going to see the deputy too quickly. And this gives you enough time to kind of see everybody else just by coupon collector arguments. Being able to do this means that this leader, who has to do a little bit of cleanup at the beginning because there were other leaders that were out there before going and messing with the population, you can clean up the state of everybody just by walking through and resetting all the other agents. You can then use the other agents to implement unary counters by just striping values across them, distributing tokens as tally marks. You have the ability to increment these counters by adding more tokens, decrement them by removing tokens, and test for 0 by just waiting until you've met every single other agent. And if you've got counters that you can increment, decrement, and test for 0, we can use some standard old results of Minsky from the 1960s to say, well, that's a log n space Turing machine. And we can simulate that as long as we're willing to tolerate a small probability of failure because our clock might not be good enough, and a significant slowdown because we're kind of doing everything in unary. All right. In some later work, we showed how to speed this up a little bit. The idea was we were still going to store all the values in unary. We're still going to have a single leader. In this case, because we couldn't figure out how to reset the population in any reasonable fashion, we assume that there is an initial leader and that we start off in a configuration with a unique leader. And so the idea now is that we're going to have communication between the leader and the other agents be done by propagating epidemics through the population, which I'll talk about a little bit more in a moment. And we're also going to build in a faster version of that phase clock that previously involved waiting for me to see the deputy, so that we can run all of this at about log n time units per step of the machine that we're simulating. So what we're relying on here is that there are very tight bounds on the propagation time for an epidemic. So an epidemic process, which we've, I guess, been getting some more experience with recently, is just a process where we have, when an infected node meets an uninfected node, and now we have 2 infected nodes. And assuming that this is all that's going on and we don't have anything else constraining this, it's easy to show that this will spread to all of the agents with high probability in theta log n time. And that's both an upper and a lower bound. All right, it's n log n interactions. And in both cases, the bound kind of comes out of concentration bounds on coupon collectors, I think is the easiest way to prove it. And the nice thing about this, though, is that if we're waiting for an epidemic to finish, we know pretty much how long we have to wait because it's not going to run more than log n time. And if we're trying to figure out how long to wait for an epidemic to finish, in a sense, we can time it using a second epidemic because we know that that second epidemic isn't going to complete too quickly. All right. And so our instruction cycle now is going to be that the leader goes and sends out some operation to all of the agents, propagating it via this rumor spreading epidemic process. And then locally, the other agents who are holding the values of these counters can implement operations like setting a counter to 0 or adding one counter to another or testing for 0 or things like that, just by doing local updates to their own state. You know, there's a little bit of implementation details for things like addition, like what do I do if I get 2 A tokens? I have to find somebody to pass one off to. But if you're careful, you can make all of this work as long as your counter values don't get too big. And in the case of getting information back to the leader, there we're just again using epidemics. Whoever has a particular token, if we're asking, is there an A token out there, can just start a new epidemic that overwrites the first one saying, yes, I have an A token. And the leader can detect whether it's there or not based on whether this counter epidemic comes back. All right. The only thing that's a little bit messy is that in order to make this work, the leader has to know when it's safe to start the next cycle. So we don't have multiple instructions kind of going out on top of each other. And for that, we built a phase clock, which was again based on this idea of epidemic propagation. Typical configuration of the phase clock, we have agents in this cycle of values mod M. The leader is sitting out there in the front and may have a few agents that's pulled up with it. And in general, when I see somebody who's in a phase ahead of me, I'll jump up to the phase that they're in. So later phases propagate like epidemics over earlier phases. So we can use the epidemic analysis to see how quickly they propagate. And what causes the leader to advance is when it sees another agent in its own phase. And it's likely that if that happens, that this phase has gotten reasonably populated with other agents. Every now and then, the leader will just happen to see the one other agent in the same phase and jump ahead. But most of the time, in order for the leader to jump ahead, we have to get a polynomial fraction of the agents to be in this phase. And we know from these epidemic bounds that that's going to take time proportional to log n before that happens most of the time. And if we have enough phases running around this clock, the rare cases where some phases happen very quickly or happen a little bit more slowly, those average out. And again, we can apply concentration bounds to make this work. All right. And we end up with something that looks like this. This is actually a fairly old plot. It dates back to the paper from 2007 or so, but they still had the data lying around. And here we see I think 8 phases. Each line represents number of agents in some phase. Some of them are a little bit thicker than others. Some of them are a little bit thinner than others. But the important thing is if we focus, say, on just the 0 and 4 phase, is as long as we're looking at phases that are far enough apart from each other, we get no overlap, which prevents this thing from eating its own tail and gives us this fairly consistent clock, with nice regular clock ticks, a little bit of variation that we can then use to time these epidemics and make everything else work. And this has been the basic structure for a lot of the work that people have done in this kind of randomized model. You build a phase clock and then use that to time other stochastic processes out there that you're engineering. All right. So what we got out of this is that, we're no longer bound by this limitation on semi-linear predicates. We have a notion of time, and now engineering population protocols becomes an issue of engineering stochastic processes and looking for interesting stochastic processes that have this kind of pairwise interaction structure. So an example of this, which was actually rediscovered a couple of times in slightly different contexts, is an algorithm that these days usually goes by the name of third state dynamics. And the idea here is we want to compute the majority of the initial population, but we want to do it very quickly, and we want to do it without assuming an initial leader. And so this is a very simple algorithm. You start off with nodes that are blue or red. These are the ones that we're trying to find the majority. Is the majority blue or is the majority red? And then we have this third blank state, which I've represented here as just a white token. And whenever a blue node meets a red node, one of them will drop out and become blank. More or less the same thing works if they both become blank, if you want to have a symmetric version of the algorithm. The main reason we only have one dropout in the standard version of this is that it avoids any possibility of losing the last 2 nodes and ending up in an all blank state that we can't get out of. All right. That process here of having nodes become blank, that is actually symmetric between the blue and red nodes. So this doesn't create any pressure towards or against the majority value. But the second part of the transition relation says that when a blank node meets a colored node, some highly opinionated person, the blank node says, well, I don't know, it sounds like you make sense. I will adopt your views. And since you're more likely to meet somebody from the majority than you are from the minority, this actually does create pressure in favor of the majority value. All right. And so this protocol, which, we had in a paper in DIS 2007, me, Dana Angluin, David Eisenstadt, and was also developed independently by Perrin, Vasudevan, and Voinovich in a paper in Infocom 2009. It has this very nice behavior. Here I have a picture where I actually started out with an equal number of, I guess, blue and purple nodes. The colors here are not perfect, and the green here represents the blank nodes. That initially you get a lot of blank nodes out there because you need them to make progress. But what happens is even with a small initial fluctuation, that pressure towards the majority node quickly drives the majority value to dominate all the values out there. And after, in this case, I guess 17,000 interactions in this population of, I think, 1,000 people, everybody has the initial slight majority value, and the blank nodes and the minority value nodes have all been driven out of existence. And in fact, we could show that with high probability in order log n time steps or order n log n interactions, this would converge to a uniform state where everybody has the same value with very high probability. And there, we initially had a bound not quite as good as this, but a very recent paper by Ann Condon and her co-authors showed that if you have an initial majority gap of at least root n log n, or sorry, where root n and root log n, that this would converge to the correct majority value, also with high probability. So it's not a perfect algorithm because you can get initial fluctuations if you have a small majority that obscure that small majority, but as long as your initial threshold is large enough, it actually is fairly useful. It's so useful, in fact, that we didn't really even invent this algorithm. This algorithm is 2.7 billion years old. There is a paper by Luca Cardelli and Attila Sikasnagi from 2012, where they observed that there's this mechanism that is used in controlling division by eukaryotic cells, what we're carrying around inside of us, called the cell cycle switch. And if you squint at it just right and fudge out, I think, one of the intermediate chemicals, this looks almost exactly like the three-state approximate majority algorithm here. All right, so independently invented by a lot of people and even some things that weren't people. Okay, so here's the story so far. We started off with this model that was in some sense too weak and threw in this random scheduling thing, which gave us the ability to do a lot of new things that we couldn't do before. But there's still some annoying features of what we got out there. The big one, I think, is this assumption that we have to have an initial leader in order to do our fast Turing machine simulation. Although, the ability having to do approximate majority instead of exact majority is also a little bit annoying. And so an obvious question is, could we do better than this if we were smarter? And it turns out the answer is no. Even being smarter does not really get us away, at least from the leader issue. And we know this because of two rather nasty impossibility results for finite state population protocols that were proved about 5 or 6 years ago. And the first of these said, okay, that issue that you had with not being able to detect termination, that is a fundamental unavoidable issue. If you start off with a dense initial configuration, which means that any state that appears in the initial configuration appears in the constant fraction of the agents, which is pretty much specifically a way of ruling out, salting the initial population with a special leader agent, then every possible state that you could reach on some agent is going to be generated within the first n interactions, within the first order 1 time units. Mostly what this comes down to in terms of the actual proof is that for any state you can generate, there's a constant depth tree of interactions that generates that. And just on sort of standard random graph kind of arguments, if you calculate the expected numbers of trees of interactions of exactly that structure that are going to happen in this population, you get a constant number of them or constant fraction of them. And this is bad because if you have some special state that says, okay, we have successfully elected a leader and we've completed phase 1 of our protocol, time to move on to phase 2, we have 5,000 agents sticking their hand up at the very beginning of the protocol saying we're done and we can now move on. All right, so it really kind of excludes a lot of these protocols that are based on trying to construct sequential executions of one protocol followed by another because everything falls apart right at the beginning of the protocol. Even worse, the second result of Doty and Soloveichik showed that if you want to even elect a leader starting from this dense configuration, and you want to do it in the stable way that guarantees that you don't ever get into a state that has 0 leaders, which turns out to be important, but most of the time you don't want to have that happen, that's going to take you omega n time. If you have a protocol that runs faster than that, there's going to be some execution that occurs with reasonably high probability where just all of your leaders are lost and then you're stuck. The protocol can't make progress. And omega n time doesn't sound like a lot necessarily if you're used to sequential algorithms, but remember we're dividing by n before we get this omega n. So we're talking about real wall clock time here. And if we're doing molecular computation and we've got a mole of agents, and n is like 6 times 10 to the 23rd, this could be quite a bit of time to wait to elect a single leader. All right. So this was all kind of terrifying. But fortunately, we have this flexible model. We can always adjust things in order to make things a little bit easier. So let's go and fix it one more time. So what's the fix? Let's get rid of the finite state assumption. All right. Recall that we had the finite state assumption because we were terrified of accidentally implementing a Turing machine. But maybe if we make that like polylog state, we can still get some interesting behavior without completely collapsing everything. And so that's what people have been doing for about the last 4 or 5 years. There's been a lot of work, kind of a second wave of population protocol results that pretty much all come down to going and dropping this finite state assumption that, we, the older generation of population protocol researchers, thought was tremendously important, but the younger folks working on this didn't see the point of. And this was actually first suggested as early as 2011 in a paper by Katsayanakis et al. And they were looking at this in the case of adversarial scheduling, and they proved this very nice space hierarchy theorem or something like that, where they showed that every additional increment, I think by log n factors in space, gave you additional power. And in particular, there was a sharp threshold that happened at log n states where below that, the semi-linearity impossibility bound still applied. And at log n, you started getting more power. And once you got all the way up to log n, then you could start building Turing machines again. All right, so it's already known that in the adversarial scheduling model, having more space would give you more power. What's been happening recently is people have been looking at what happens when you have a little bit more space in the random scheduling model. And the big thing that happens here is that suddenly you can build these phase clocks that previously required a unique leader without assuming a unique leader to act as a bottleneck. And the first example I know of for this was something from a paper that I did with Dan Alistar and Rati Gelashvili, where we were using the power of two choices idea that shows up in these sort of balls and bins problems, where instead of just throwing a ball into a random bin, you pick 2 bins and then throw the ball into the lighter bin. It's very easy to implement that in terms of a population protocol. There are known results that say that the difference between the largest and the smallest bin stays within log n with high probability when you do that. And we could just go do that and say, okay, we're going to have this phase clock where if we add up the numbers over all of the agents, it advances by exactly 1 per interaction. So advances by, I guess, the average value advances by 1 per time unit. And since we know that the minimum and maximum values are within log n of each other, we can wrap this around in order to implement this in bounded space. And once you've got a phase clock with no leader, you can use that to do leader election. You just have the leaders send out epidemics to each other saying, hey, I believe I'm the only leader and my random bit is 0. Is there anybody with a random bit of 1? And the 1 guys win. And pretty soon you're down to a single leader and they can detect that they're there by themselves. And there's been some very nice subsequent work doing variations of this kind of idea, a lot of it by Gosnich and Stokosiak and Uznansky, and then later Kozovsky and Uznansky, that showed that you could actually reduce the space and time complexity of this, even down to order 1 states and polylog time in the case of this Kozovsky and Uznansky result, although you have to give up the guarantee that you never end up with 0 leaders. You just make it something that can happen with very low probability. All right, so a lot of progress on that front. Another issue that comes up when you start dealing with larger state is that if my state now depends on n, there's this question of how n interacts with my transition function. And in particular, if my transition function is allowed to know what n is, or if I just have to have some transition function that in some sense gets truncated down to whatever the actual value of n is, but n isn't baked into the transition function itself. A lot of these results that I talked about in the previous slide do in fact assume that the agents have some idea of what n is. So for example, for the power of 2 choices phase clock, if I don't know what log n is, I don't know where to wrap around. So there's been a lot of recent work on looking at how to do counting in the context of a population protocol. The first big result on this was a paper by Doty et al. From about 3 years ago in DISC. And they showed that using polynomial states, which is still only log n bits, but if you express in terms of states, it's scary. They could count the size of the population exactly in log n times log n time. And subsequent work on that is look more at approximate measures, where you just want to get an estimate of log n plus or minus a constant, equivalent to getting an estimate of n, times or divided by a constant. And that's gotten some nicer results here. There's a very recent survey on this, which if you're interested, it's probably worth looking up, just came out a few weeks ago. And so this is still an active area of research that people are looking at. Okay, so here's kind of where we are now. Um, we're now assuming we have a collection of small state agents. We still have this interaction model, which involves pairwise interactions under control of a, kind of an unpredictable process. But the unpredictable process is now random because that's kind of easier to deal with. And we can also assume, because we have these protocols for electing leaders and for estimating log n, that if you want your protocol to know what log n is or start with an initial leader, you can just run one of these protocols first, and with high probability that will start you off in a config, or when that finishes, you can then start off in a configuration where you can run whatever other protocol you want with the assumption that these things are out there. All right, so that's kind of the current state of the art of where we are. All right, so this model's been moving around a lot. I've been describing several variants of this model that I claim are all basically the same model. So in order to make that claim, I think I need to point to some core of the model that hasn't changed despite all these other tweaks we've been doing this. And I think the main thing that we have here is this idea that we're trying to do distributed computation where we don't have any kind of addressing. We have no sort of communication structure out there. So population protocols are what you get where you take your distributed system and drop it into a blender and make everybody forget their own name. And if we keep this part, there are still a few other things that are kind of holdovers from this initial finite state assumption that we might be able to ask, well, can we get rid of those too? Like, for example, maybe we can allow very large states, or we can allow arbitrary agent IDs. And what made us afraid of this was this idea that, well, if I have large states and agent IDs, I can build a Turing machine by just lining all my agents up and calling them a Turing machine tape. And I can even use some of these tools like epidemics and a phase clock to do this fairly quickly, where, by using an epidemic to propagate control signals between the controller and the tape, I can do each step of my Turing machine in log n time. But if I do that, then I'm in some sense taking this embarrassingly parallel model where all these interactions are happening simultaneously. And because I'm constrained to use these epidemics kind of sequentially one after the other to implement my Turing machine, I've suddenly turned it into a very sequential model. And this is very disappointing. So I'd like to ask, what can I do, say, in parallel in a model like this? Now, if I get too carried away and allow unlimited states, I can do anything because I can just have everybody broadcast using, n parallel epidemics, what their input is, and then compute whatever I want locally at each agent. So if I allow, say, a super polynomial number of states enough to keep all this information around, then again, things don't get very interesting. But I think there's an intermediate case where I have a polynomial number of states, log n bits worth of states, where I can no longer do this. And now, in a sense, what I'm doing is I'm trying to do computation where I'm building essentially a circuit with random structure. So if I think of each interaction that I do and the state of an agent as a result of that interaction as representing a gate in the circuit, it depends on the outputs of two previous gates or two previous interactions. And so any population protocol that runs in polylog time, I can in a sense translate into this randomized NC circuit, where NC is the class of circuits that run in polylog depth using polymany gates. And I think the interesting question here is, to what extent can I do the reverse? If I have, say, something that I can compute in NC, or possibly some restricted class of NC, like the symmetric predicate, since I don't have the ability necessarily to identify specific inputs, is there some way I can encode that using some clever trick and epidemics and whatever other tools we might have, so that despite the fact that I've got random scheduling and a random circuit structure, I can still recover the power of the original model? And I don't know the answer to that, so that's kind of one of my two big open problems that I'm going to end with this with. The other one is that, in a sense, I kind of lied about the original model because I like this idea of having no structure so much as the core of the model, that I left out this very important detail that showed up in the original paper and then was largely forgotten for 15 years after that, which is that we actually allowed you to impose an interaction graph on a population protocol that said only adjacent agents can interact with each other. And this was a way of trying to model spatial constraints. Maybe as my cows are wandering around in the field, there's a fence in the middle that keeps some cows from interacting with other cows or something like that. But you can imagine a class of population protocols where you have restricted interaction graphs. And there's some early results that showed, for example, that this didn't give you any extra power because you could always have the states wander around between agents until they ran into each other just by luck, instead of requiring that the agents themselves physically wander around. And in some cases, like where you had a bounded degree graph, you could impose enough structure on top of that to kind of thread a Turing machine tape through all the nodes and get the power of a Turing machine. And for that reason, I think people sort of forgot about this version of the model for a while. But recently, there's been a very nice paper by Alistair Gelashvili and Rybicki that's going to be in the upcoming POTSI, where they said, wait, this actually might be interesting if we're looking at this in the context of randomized scheduling, which was never really considered back in the old days. And so they have a couple of results showing various simulations between different kinds of graphs and relating what you can do on a particular graph to conductance properties of that graph. And I think the interesting general question here might be just what can a population protocol learn about the structure of its underlying graph, or just more generally, the whatever scheduling regime that it's in, given both that it needs to observe that underlying structure through the scheduling decisions just to see what's happening, and also that that underlying structure affects what kind of power the populations the protocol itself has. All right, that's all my slides. So if there are any questions?